Let's talk a bit about gravity. Gravity is that mysterious quality that matter has that draws all objects with mass closer and closer to each other. And isn't it nice in this world where so many things, from politics to religion, are dividing us, that something can pull us together? And that's gravity. You see, gravity is what holds the moon and the earth together. That's a picture of the earth taken from the moon. Gravity is what causes a hammer to be drawn toward the ground when it's dropped. Any objects with mass are affected by gravity and are always pulled together, not pushed apart. In fact, sometimes objects without mass are affected by gravity too. Einstein's general theory of relativity back in 1915 speculated that gravity would affect the path of light. And sure enough, in the eclipse of 1919, light was visible that shouldn't have been because it was bending around the sun. It was affected by the sun's enormous gravity. So gravity affects a whole lot of things. Many times when we think of how gravity acts, we think, well, maybe we can defy the law of gravity, but that fails every single time. For example, Wile E. Coyote consistently tries to defy the law of gravity, and he's always wrong. It always gets it. Now, it doesn't work necessarily that way where you only start falling once you realize there's nothing underneath you holding you up. Gravity works all the time on all objects. Gravity causes things to accelerate. It causes motion to change. The amount of acceleration of gravity is shown here. When we talk about the amount of gravitational acceleration, near Earth's surface, it's 9.80 meters per second squared. That's meters per second per second. But it can also be written as 32.2 feet per second squared because there are a little more than 3 feet in a meter, and 9.8 meters is about 10 feet, so it kind of works out. Notice the word down. Gravity is in fact a vector, so if we wanted to, above this little a, we could put acceleration. Lowercase g is often used to symbolize this amount of gravitational acceleration, never uppercase g. And remember, this amount of acceleration is always what we have when we're near Earth's surface. Not when we're 100 miles above the Earth, not when we're on the moon or on Mars, but near Earth's surface. But since that's where all of us are right now, for the most part, that's the number that we're going to use. Special thing about gravity is that the acceleration of a falling object doesn't depend on the mass of the object. Heavier objects don't fall faster than lighter objects if we ignore air resistance. In fact, here's an experiment you can try. My students have tried it. What we would always do is take out a heavy object like a shoe or something like that, and a light object like a sheet of paper, and we drop them at the same time. What do you suppose would happen? That's right, the shoe would hit the floor first, obviously. But eventually some bright student came up with the idea that maybe it was the air resistance, what we call aerodynamic drag, that was keeping the paper from accelerating as rapidly as the shoe. So then we had to put out there what would be a solution to this. How could we do a more fair test? Eventually some student came up with the brilliant idea that if we just crumple up the sheet of paper into as small a ball as possible and then drop it along with the shoe, maybe they would fall at the same rate. I encourage you to try this on your own at home. The person who discovered this principle was a fellow by the name of Galileo. Perhaps you've seen some idea of this, like here. This is, in fact, a representation of Galileo's famous experiment where he drops two objects of two different masses and they fell at the same rate. Now, the rumor, you might say the legend, is that he did this from off the Leaning Tower of Pisa. That probably is, in fact, just a legend, but he did do the experiment. He did show that his idea was true, that all objects accelerate at the same rate. We can see it a little bit more easily here. If this were a stroboscopic view of two objects being dropped at the same time, these photos are taken during the same amount of time elapse. So for example, maybe there's a quarter of a second between these two pictures, and another quarter of a second between these two pictures, and another quarter of a second between these two pictures. What you can clearly see are two things. First, the heavy object and the light object accelerate at the same rate. And second, they are in fact accelerating, moving quite slowly here, faster here, and even faster here. Remember, it's the same amount of time that's elapsed between each photograph. Galileo's principle was demonstrated pretty magnificently quite a few years ago. You see, a few years ago, we had a space program that landed people on the moon. This is Commander David Scott, an American astronaut on the moon back in 1971. I'll let him take it from there.
In my left hand, I have a feather. In my right hand, a hammer. I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here and hopefully they'll hit the ground at the same time. How about that?
How about that indeed? Galileo was right, and up on the moon, where there's no air resistance to stop it, the feather fell at exactly the same rate as the hammer. So that means if gravity has constant acceleration, we can work problems involving gravity the same way we work any other kind of acceleration problem. For example, let's suppose a rock is dropped out of a window 25.8 meters high. How much time will it take for it to reach the ground? Well, if we start this problem the way we should start all problems, what we're going to be doing first is listing our variables. In fact, before even that, we're going to have to choose a positive direction. That positive direction, in my case, I choose up. Down would work also, but I think of up as kind of the positive direction. I'm just used to that. And we list the things that we know. We know, for example, that the displacement, notice that it says delta y this time, not delta x, because we're talking about vertical motion, is negative 25.8 meters. Now, it doesn't say negative in the problem, but it does imply that the object, the rock, is going to fall, and that means it's going to move in the negative direction. The acceleration, there it is negative 9.80 meters per second squared. That's the correct unit for this problem. Is there any other information that we know here? The initial velocity is 0? Wherever does the problem say that? Well, if we look up here in the problem, it says that the rock is dropped out of the window. It doesn't say it's thrown downward or thrown upward. It is dropped. Dropped means you open your hand and release the rock. So its initial velocity is in fact 0. Finally, of course, we list the variable that we're trying to find. It's asking for time. And so that becomes our question. And so now pause the video and see if you can work your way through the problem. Okay, let's see how you did. We're looking for a formula that involves these 4 variables. And the one that I can think of that works best is the one that says that displacement is equal to initial velocity times time plus 1/2 acceleration times time squared. Is that the one that you picked out? Let's find out. Displacement is here, check. Velocity, initial velocity, is here, check. Time is the question we're looking for, check. And acceleration is the acceleration of gravity. This looks like the way to go. So when we plug in the numbers, we write in negative 25.8 equals the initial velocity, 0, times time is still going to be 0, plus 1/2 times the acceleration of negative 9.80. I'll just write it as negative 9.8. It's going to work out the same on the calculator, times time squared. Or in other words, negative 25.8 equals negative 4.9 t squared. If we divide both sides by negative 4.9, we don't get t. We get t squared, but it's going to equal a positive number, which is a darn good thing because we sure don't want to be taking square roots of negative numbers. And so this ends up being 5.265, well, actually seconds squared. So again, we have to take the square root of that. When we take the square root, you learned in math class, you get a positive or negative answer. The negative answer actually does have meaning here, but we're not going to discuss that at this time. Clearly what we want in this case is the positive answer, and it ends up being 2.29 seconds, rounding to 3 significant figures. And the reason we do that and put the unit on there is because if you look at the original data in the problem, we were talking about 3 significant figures here and 3 significant figures here. And that's it. And so as long as we realize what the acceleration of gravity is, we work the problem like any other acceleration problem. Make sense? Okay, let's try another one. Let's suppose that from the ground, a ball is tossed straight up at 18.6 feet per second. Where will it be highest above the ground? Maybe now's a good time to pause the video and see if you can list your variables correctly. Okay, let's see how you did. First thing, of course, is choose a positive direction. Up is a good choice for positive. The acceleration, oh, did you get that right? Negative 32.2 feet per second squared, because our problem is in feet, not in meters. Okay, so fix that if you had that wrong. But continuing on, the initial velocity is 18.6 feet per second. What else are we finding out? Well, we're finding out where is it highest above the ground, so we want to find its vertical displacement. We don't have enough information here. We usually need 3 pieces of information and solve for the 4th. There's something else implied by the problem. You see the ball is being tossed straight up, so it's going to go slower and slower and slower and eventually stop, and then it's going to start falling, right? Here's the thing, when it's highest above the ground, that's right there, and the problem ends right there. So this falling part isn't part of this problem, which means at the very top we have one more piece of information. You know what it is? That's right, that the final velocity is 0. We call it the final velocity because it's the final for the problem when it reaches highest above the ground. So now if you got all of that, you probably solved the problem too. If not, go ahead and pause the video again and see if you can find the correct formula to solve this. Okay, notice that time is not one of the variables. Did you choose this formula? It would be a very good choice. It's not the only way to do the problem. I'm just saying it's the most efficient way. So if we plug in the numbers, 2 times the acceleration of negative 32.2 times the displacement, which is what we're trying to find, is equal to the final velocity squared minus the initial velocity squared. So that's what we're trying to figure out. Notice that this is going to be negative 64.4 delta y equals a negative number. This is not a negative number squared. It's 0 minus a number squared. So it's 0 minus a positive number. It's negative on both sides. We get that delta y is in fact a positive answer, which is what we would expect. And in fact, what we get for our answer is that delta y is equal to 5.37 feet. Note the unit, feet, not meters. And so that's how high up it would go. Not very far, but you can throw a lot faster than 18.6 feet per second also. Get the idea? Any question about that? Keep in mind, air resistance is really at work, and so air resistance would affect these answers. We're doing all of our problems on the assumption that there is no air resistance. It takes a lot more knowledge of physics to include air resistance in the problems. But that's it. Practice a few more problems on your own and you'll do great on this. Bye-bye.